For this project, we went to the elevator at the R.H. Stafford Library in order to find how the weight of an object changes during an elevator's 4 different accelerations. Those 4 accelerations are the upward and downward acceleration while the elevator is moving up, and the downward and upward accelerations as the elevator is moving down. By taking measurements from the scale with Ibuki on it, we were able to find the normal force of the elevator on Ibuki. And this is because of Newton's third law stating that for every action, which we can consider to be the force of Ibuki on the scale and the elevator, there's an equal and opposite reaction, which we can consider to be the force of the elevator on Ibuki. After that, we combine the normal force with the force of gravity on Ibuki in order to find the total force in the force equals mass times acceleration equation. Then we can solve for the acceleration of Ibuki and the elevator. So going into the data collection, we hypothesize that Ibuki will accelerate the fastest while going down because of the help from gravity. And also we believe that he will accelerate the least while traveling upwards and slowing down because of gravity.
Going down. Going up.
For our analysis, we first had to identify the equations which we would be using to solve for acceleration. And to solve for these equations, we'd have to draw a diagram to figure out the forces acting upon the elevator. So over here, we can see the normal force acting up, or the force of tension, which is moving the elevator up and down. Then we also have the weight of Ibuki times gravity, which is acting against the normal force. In addition, we also have acceleration, which is potentially acting upon the elevator depending on if it's going up or down and before it hits constant velocity. So the 2 equations we can use to find acceleration is the total net force equals mass times acceleration, and the total net force equals the negative weight since it's going down, plus the normal force. And when combining these 2, we can get our equation for acceleration. The normal force equals mass times acceleration plus mass times the force of gravity. But it's important to keep in mind that the mass times gravity is Ibuki's normal mass and compared to mass times acceleration when it's the mass that's being read on a scale. And then finally, since the scale is being read in pounds, we have to convert pounds all the way to kilograms by using this equation. So in order to first solve any of our acceleration problems, we have to first find what Ibuki's weight is in kilograms. And beforehand, we measured him out as 174 pounds on the scale. So by doing our conversion from pounds to kilograms, we measured that Ibuki is 78.92 kilograms. And then moving over, we first calculated the acceleration of the elevator going up when it initially speeds up. And the chart we drew here shows that with acceleration going up, normal force going up, and then the weight acting against the normal force. So when we measured Ibuki's weight when the elevator was accelerating going up, we found that he was 186 pounds. And by doing our pounds to kilogram conversion, we found that Ibuki was 84.37 kilograms. So now, once we know that Ibuki's weight is 84.37 kilograms, we can find the normal force, which is his weight in the elevator times the force of gravity, which is 826.8 newtons. After that, we can use the equation we discussed earlier to find the acceleration of the elevator when it's going up and speeding up. And so we plugged in the normal force equals Ibuki's weight when adjusted for acceleration times acceleration plus his initial weight times the acceleration of gravity. And we found that the acceleration of the elevator was
633 meters per second squared.
So the second acceleration that we're going to be finding is the acceleration of the elevator when it's going up but slowing down until it stays at rest. So for this set of data, we found that Ibuki was 159 pounds when the elevator started to decelerate, which going through our formula again is 72.12 kilograms. And then multiplying that by the force of gravity, we found that the total, the normal force of the elevator is 706.78 newtons. And then for this equation, it's actually different than the previous equation because acceleration in this case is negative because it is decelerating and moving more towards zero. We had to use negative MA to account for the negative acceleration. And when we plug in all of our data, we found that the acceleration in this case was 0.924 meters per second squared, or 0.924 meters per second squared heading in the negative direction, or just negative 0.924 meters per second squared. So for our final two accelerations, they follow similar.
I'm just gonna keep recording, just go whenever.
For our final two accelerations, we use similar formulas as per the last two accelerations. And in this case, we're going to find the acceleration going down and speeding up. And when Ibuki was in the elevator, we found him to be 164 pounds. And when plugging in the equation, we found he was 74.39 kilograms. And then when multiplying by 9.8, we found the normal force to be 729 newtons. We're going to use the same equation as the last one. Normal force equals the negative mass times acceleration plus mass times the force of gravity. Because in this case, again, as we can see over here, the acceleration is working in the negative direction as it is speeding up in the negative direction. So when we plug all of the numbers in, we get the acceleration to be 0.597 meters per second squared in the negative direction, or negative 0.597 meters per second squared. And then for the fourth acceleration, it is exactly the same as the first one because we found his weight to be 186 pounds when slowing down, going down, and that turned out to be 84.37 kilograms. Multiplying it by 9.8 again, we found the normal force to be 826.8 newtons, and then plugging it into the regular equation, Fn equals ma plus mg, because acceleration is working in the negative direction even though he's going down. We found his acceleration to be 0.633 meters per second squared. So with all of these accelerations now calculated, we have our four accelerations here. The acceleration going up and speeding up, which is 0.633 meters per second squared. The acceleration going up and slowing down is 0.924 meters per second squared, or negative 0.924 meters per second squared. And then the acceleration going down and speeding up is negative 0.59 meters per second squared, or 0.597 meters per second squared going in the negative direction. And the acceleration going down but slowing down, which means it's working in the positive direction, and that is 0.633 meters per second squared.
In conclusion, these are the four values of acceleration in an elevator we found. 0.633 in the positive direction, 0.924 in the negative direction, 0.597 in the negative direction, and 0.633 in the negative direction. The largest acceleration was 0.924 when the elevator was traveling upwards while it was being slowed down. This is because to get the elevator moving, it requires the most force to get it started. So when it's trying to slow it down, it requires even more force to then slow it down to a stop. The slowest acceleration was 0.597, which was when the elevator was traveling downwards and the elevator was speeding up. This is because since it's going downwards with the force of gravity, it requires less force to get it started and moving. While the velocity is constant in the middle of the elevator trip, the acceleration is zero because the net force of the forces are zero. Our hypothesis was wrong because we stated that it'd be fastest going down while speeding up, when in fact it was the complete opposite, and it was the fastest while going up and slowing down.